A because he used the spelling that is the British spelling, not the American spelling of our institution.
Which of the two is official, actually? Which of the translations is official?
Official is center 4. Center 4. Nevertheless, we can begin now. He will tell us about topology, graphs, and indistinguishable parts.
Ta dyskusja się toczyła kilkanaście lat temu. Tak.
Okay, so this is a
To może być przesada.
This is a joint project that I'm doing with Tomasz Maciążek, which is affiliated here in the CFT and also in University of Bristol. And so the first part of this project was his PhD thesis, and what we are doing now is the continuation of this. So by topology, which as I will explain later, by topology we mean the homology groups.
What group?
Homology groups. Okay. So the first about motivation.
You are aware that there might be some deprived intellectual individuals like me who may not understand these words. So.
Okay, but I will try to explain everything in simple words. Like homology groups describe holes in our space. So intuitively, it's possible to explain. Okay, so about a few words about motivation. So our motivation comes from topological description of quantum statistics. So when you have a system of indistinguishable particles, then we can impose when we construct wave functions on some configuration space, on some topological space, and we put n particles on this space. Then we can consider a symmetric part or anti-symmetric part of this of the corresponding Hilbert space, but and then we have the symmetry that when we permute particles, then we have some phase in front of the wave function. So some global phase.
But that was not noticed before 1977.
Yes, sure, of course. But these guys.
Not only noticed, but also used.
Yes, but these guys actually they have noticed that we, instead of just considering like a flat Cartesian product of configuration spaces, so this imposes some relation on a Cartesian product of two spaces when we permute particles. So you want to impose this relation on the classical level. So what we do is we take, so let's focus on two particles first. So X is a one particle configuration space. When you put two particles, we have X Cartesian product with X. We don't want the particles to collide, so we subtract the diagonal. So these are these will be points.
But this is a problem because sometimes it is better to not to throw it away.
Yes, so I mean, so
it is a delicate.
You mean delta? But this is a measure zero set.
So what? But topology is topology.
Okay.
Yes, but it still has the same singularity. So if we do not subtract
The other problem, which of course is much simpler, is that these particles
In
are
particular,
not subject.
bosons have a tendency to be on delta. Therefore, throwing them away, we lose a lot.
Yes, but somehow in this, yes, of course, but in this model we somehow assume that we don't want them to be at the same place at the same time.
And also those particles are completely free. There is no magnetic field or anything in this configuration space.
No, not yet. It's,
Wait a moment, this is kinematics.
It's just kinematics.
But kinematics only for scalar parts.
Yes. Yeah.
Sorry?
This is kinematics, but only for scalar parts.
No, I mean that if you
Because
have a
for
two-dimensional space and the
Yes,
particles
it's only for scalar fields. Yes.
completely kinematic, but there
Only
is
for
an
scalar
external
level
field,
function.
then this expression is not valid.
Okay.
Because in two-dimensional world you will have this additional quantum number, so to say, related that if you move the particles around in a magnetic field, you also have to add the phase of the magnetic field. So that's what the anyons came into existence.
Okay, so
Quantum Hall effect exists.
okay, but at this moment we just subtract the diagonal and take the quotient by the permutation group. So this is just we group points which are x1, x2 is identified with x2, x1. So we get some non-trivial space which has some singularities which arise from this diagonal. And also it has a nice property that loops in this space may describe exchange of particles, because it means that particles were at some configuration, they did some movement, something happened, and they returned to the same configuration modulo the permutation. So they could exchange during this movement, during this process.
So that excludes the loop which starts in one point and comes back to the same point.
No,
It's
the loop is that it comes to the same point.
So maybe let me show you an example of two particles in R2. So how to describe this C2 of R2 easier. So when we have vectors x1 and x2 in R2, then we can extract the center of mass, which is x1 plus x2 over 2, and also we have a relative position, which is x2 minus x1 over, maybe not over 2, but modulo some factor. It's the difference of the two positions. So note that this is invariant under the permutations. So this S2 group doesn't preserve this part, so it factorizes as R2 here. And the relative position, we can draw it as a plane. This is the plane of relative positions. And when we have a point x r and minus xr, then this point is identified by these two permutations. Because those 2 points mean that this is the same configuration which is switched, where the particles were switched. So we have two kinds of loops. One loop is when the particles aren't switched, and this is a contractible trivial loop here. And there's another kind of loops when we have to identify both endpoints.
That is topologically is also a loop then.
This is also a loop.
Yes, but you have removed zero from this space, therefore topologically this is different. In the space of relative positions, he removed zero, and therefore it is
So
topologically...
one loop surrounds zero and the other loop does not.
Yes, and this one is not contractible because there is this zero.
And this is the fundamental difference between 2 and 3 dimensions. Yeah?
Yes,
And
also
this is
yes.
why
Yes.
anyons exist only in 2 dimensions.
Yes.
Exactly. So when we want to have a physical model which would describe the situation, this would be this fractional quantum coordinate.
But you may also surround the zero several times.
Also, yes. So this would be also a non-contractible. Okay. So loops when those particle exchange are non-contractible. So when we make a translation of a wave function around such a loop, then it may, in some situations, result with some phase factor, with multiplication of some phase.
Nie, muszą być tutaj. Skalarne, bo inaczej
So for example, the same situation happens in the Aharonov-Von effect when we have a call in a disk and we translate the Fourier function around this loop. Then it results with this multiplication, which depends on the flux of the magnetic field. And also we want to impose some natural conditions on this phase. So when we travel around this loop n times, then we want this phase to be n times phase when we travel once. And also when we add two loops, and how do we do it? So when we have one loop and another loop, then the sum would be going around here and then going around here, like an 8 number, 8 or infinity symbol.
But if this center point is excluded, then you cannot have this picture because this point does not exist.
But so suppose it is a good point. I mean, it's just one. It's just one point in this space. I mean, it's not a singular point.
It's away from zero.
It's away from zero.
It's
Yes.
away.
Or of course we can also have something like.
Sorry, I came late. Perhaps you explained this, but why do you exclude this zero for bosons?
It's just our model. We just do not want the particles to collide.
It was already discussed.
Well, but I came late.
So
The answer is because this is just such a decision has been made.
But you are aware that in reality that's not a very good assumption.
well, yes, yes.
Okay.
This
Depends
also
on what
was
they want to
discussed.
discuss.
But they want to discuss model which is not applicable to just atoms.
Yeah. But it has some realizations. Okay. Anyway, so in this, when we want to have this non-contractible loop, then a sum would mean that we go here, and then we go here. So this would be a sum of two loops. So we want also those phases to add up. So we see that here there is some abelian representation of loops. So in mathematical terms, so precisely you are interested in abelian representations of the first fundamental group. So the first fundamental group is simply a group of loops. So and this exactly is described by the first homology group. So let's just say that this is the definition of the first homology group. So what happens when you take R2, not just the plane, then we get that the first homology group is Z2. So it means that there are only two abelian representations, and one with phase E to I phi, which corresponds to fermions, and one with phase 1, which would describe Boson's symmetry functions. And in R2 we get there is a whole infinity of possibilities, and so any phase can be associated with a loop, and this gives rise to n statistics. And if you want to go one dimension lower, then we have R, but there is this problem that particles always collide on a line. So one way to go around this is to consider graphs. Because here, for example, we can have one particle here and then another traveling here, or we have junctions which allow a particle exchange. So for a graph, when you put many particles on a graph, then it's the configuration space is the Cartesian product, n-fold Cartesian product of these graphs. And as a graph, I mean a subset of R2. Of R2. So when I take this Cartesian product, it's
planar graphs, not graphs in 3 dimensions.
or R2 or R3. It's just to. I just wanted to say that in this Cartesian product, we also consider products of edges, which gives rise to squares. Okay, it's not just Cartesian, because there is also another notion of Cartesian product of graphs when you take only vertices. So this is not this one. This is just
Yes, but my question was Do you consider graphs in 3 dimensions or
Also, yes, non-planar graphs also.
non-linear?
Yes. And we subtract the diagonal also, which is the set of all points on the graph. So we can also consider points inside here, inside every edge. All points which were 2 coordinates, at least 2 coordinates per side. So we know that this group, which describes the quantum statistics, is a finitely generated abelian group. But there are 2 parts, of which only one is relevant actually to our approach. So the first one is like a trivial one, which I'll explain later. But this part is quantum statistical part, and here we can have this Z2 or Z for anions, Z2 for bosons, and many different things which correspond, which depend on the connectivity and on the planarity of the graph. So what a planar graph is? A planar graph is just a graph which you can draw on a plane. A non-planar graph would be a graph which cannot be drawn on a plane. An example of such a graph is this thing, which is called K5. This is a graph which cannot be drawn on a plane without self-intersections.
So it's a full graph? This very example is just full graph, everything is connected with everything?
Yes, it's on 5 edges. So this would be planar, this would be non-planar, and what is the connectivity? So 2 connected would mean that we have, for any 2 vertices, we have 2 independent paths in a graph. Inside, they do not have any common parts inside. So there are 2, for 3 connected, there are 3 independent paths, etc.
At least 3 or exactly?
At least 3. Yes. So what are the results? And this is the work of Adam, and the results are that for one connected graphs we have many anion phases, and they depend on the number of particles, and it's not a very nice situation. But for 2 connected graphs, the quantum statistics do not depend on the number of particles. So when you have more than 2 particles on a graph, then the quantum statistics is always the same.
What does it mean that the quantum statistics is the same? What, in
Like,
physical terms?
In physical terms, when you look at those loops, then the phase, there's always the same number of those abelian representations of loops. The number of different possible phases is the same. It stabilizes when you have 2 particles, and add more, then you have the same number of phases.
I have a question, because in standard courses of quantum field theory, it is said that quantum statistics originates in relativistic causality. Yes, and here your approach suggests that it is connected. It originates rather in topology of configurational space. Okay, so what is the relation between those two?
There is no. There is absolutely no spin here. So
yes, there is no spin, but still we have quantum statistics. Yes,
but only for scalar particles, which but does not connect with quantum field theory, where the main theme is that the fermions are described by antisymmetric.
Yes. So there was some
no metric structure, therefore no possibility to even to say what is.
So the action of the Poincare group is a very important thing in this statistics. Yes, but here we have. Here you don't have the Poincare. Yes, but here we have spinless particles, and we still have 2 possibilities: fermions and bosons. Yes. So
which means that
yes, he said that
fermions.
No, he said that there are 2 possibilities.
But fermions have spin.
No, but 2 possibilities: symmetric and antisymmetric part of the scalar wave function. Yes.
Yes, I mean there were some attempts to somehow extend this this geometric approach to spin, to particle spin, and it has been a long-standing problem, and I've heard that it was solved like a month ago, so I don't know what it was actually this. But there were some serious problems. So, for example, how to impose a proper metric and.
So, to summarize, your assumptions are too weak, so to say, to discard fermions.
Yes, discard fermions.
And anions also.
Yeah. Okay. So continue that for free connected graphs, we have the situations that they resemble R2 or R3. So when we have those statistics on free connected graphs, when a free connected graph is non-planar, so which means that it can be embedded in R3, then the quantum statistics are the same as for R3. Or if it is planar, then we have, so it can be drawn on a plane. It has a rather a form of pseudo two-dimensional thing. Then the quantum statistics also say that it behaves like a plane. So we have also aims. And some examples of those graphs. So this would be a one-connected graph, which is called a star graph. A two-connected graph is here. This is like a circle, a cycle. A three-connected graph is here. It's a complete graph with 4 vertices. This one is planar. And the non-planar graph, the three-connected non-planar graph is this one.
And is it interesting to ask what happens for 4 or 5 connected graphs?
Well, so if we have if the connectivity is larger, then it's true, right? It's like for three connected. It's three connected, or at least 3.
Yeah, so it's enough.
Are those graphs in any sense related to the pictures of the crystallographic group? We have, I mean, in this whole business with anyone's, not anyone's, they have nothing to do with chemistry, was related to the behavior of the particles on a special kind of lattice. And I hardly can imagine a honeycomb two-dimensional lattice constructed from your objects, right?
So it's like one.
So in physics, I mean, there are no particles in 2 dimensions. I mean, you have to manufacture them somehow.
Yes. Actually, it's one of the biggest problems at the moment with this project, that we cannot, at least we were not able to construct a proper physical model that would realize the statistics in graphs.
No, but you can have wires and electrons.
Like 2-dimensional gas.
Running along these.
But the anyones are not the particles which move on the wires.
That's right.
They are not
In
the
some sense
particles.
they are in between, but in some sense they are in between.
Yes, somehow they are not on the wire.
That's right.
And what about...
They sit in the middle. I mean,
But now we talk about graphs.
Yes.
What about...
I have nothing against the graphs. I love them and I can worship them. The only problem is that in the physics, if I would like to see, I would like to make one of those models in the laboratory.
Yes, one model, for example, is what Leszek Szylko does.
Oh, yes. Minister Szylko. Yes. So I would just to make a question. Is it at all related to the microwave?
My insurance does not allow me to question the achievements of the ministers.
No, but our co-authors we can. So we have microwaves, which propagate along different waveguides, which are connected and form such a graph-like structures.
So as far as I asked this question,
but these are not particles; these are microwaves.
So these microwave graphs, they correspond to only one particle.
Exactly. Yeah, that has nothing to do. I mean, this microwave experiments have nothing to do with this.
Graphs could be similar.
Yeah, but the graph. I mean, there are graphs on the walls all over the Warsaw, but they are not related to these problems. So, I mean. We cannot ask arbitrary question in the relation.
So is there any physical system that this could be applied to?
Not yet.
No, not yet. I know that there were some tries to model it with the Hubbard model, some Hubbard models. Professor Levenstein, I mean, Adam was conducted Professor Levenstein, and they said that they can do anything, so they can model this. But when it comes to actual doing, they said that they cannot do this. So, and I know that they tried to do it with some Hubbard model. So, yes. So this is.
But I would disagree that microwaves have nothing to do with this, because microwaves are made of photons and certain bosons.
But we just discussed that bosons are for some reason.
No, bosons aren't.
But you want to make the product of the configurational spaces
Yes.
of this kind, not of photon
Yeah.
degree of freedom.
Yeah. That's the other way around.
This is the configurational space
You
of
want
one
to-
particle, and
Right,
you have
want
to
localize it.
engineer the product of these spaces, of this topology.
Okay, so and our project is now about computing higher homology groups, which I will define in a moment, and they also might have some physical interpretation, which we haven't also constructed yet, but we have some ideas. But first I have to say something more about this configuration space itself.
Just the last comment. In a sense, the use of the word anyone's here is wrong, because the anyone's have nothing to do with this graph. They are related to the magnetic field. There are no anyone's if there is no magnetic field.
Well, actually,
Right? I mean, it's the words. We are using words might be misleading. I mean, at least for some stupid.
For example, we can construct a potential on this configuration
You don't
space
need
to
magnetic
realize this. Like a discrete potential.
What?
Just vector potential you need to mimic the magnetic field.
Yeah, that, okay, I retreat the word magnetic field vector potential.
Yes.
You need the gauge field
Yes.
which
But on the lattice it can be engineered.
but it's much nicer to use. In fact, you need a magnetic field because there's no way how you can generate the vector potential without using a magnetic field.
You will do it with light.
There are many possibilities.
You can do it with light.
A light is not a magnetic
Many
field.
people make living. Yes.
Light is not a magnetic field. Remarkable. I believe
No, no.
half of it is magnetic field, isn't it? It's only a question that is difficult to tell which half.
You can even engineer non-abelian magnetic
Yes,
field,
that's right.
Yes. that
which
I
is
know.
nothing to do with magnetic field.
Yes.
Okay, so now I'd like to continue, and I have to say something more about this configuration space. So as you can see from this definition here, it's like a rather complicated thing, but we managed to draw it for such a graph. When you have such a graph, then this is the corresponding two-particle configuration space. So it doesn't have a very nice structure, and these points are excluded. These points are from the diagonal, and also these dashed lines are also from the diagonal. And all other parts are the two-dimensional or of dimension 2. Here inside, it's full inside. But we can do something to this object, which will give it a simple structure. So we can contract those parts so that they are flat, and also we can somehow blow this thing. So we are left with only with this circle here.
Exactly.
So all the topology is actually here in this one circle, and everything else can be contracted. Or in mathematical terms we say that these things can be deformed, deformation retracted, or just deformed to a simple complex, which has the same topological properties. And there is a prescription how to do it. boundary. So actually, from now on we by the Cn of gamma we rather mean this complex.
What is CW?
CW complex.
The letter CW stands for what?
W is for weak topology. It's like we are gluing the spheres. And C, I don't remember what is it.
Complex.
For complex?
No, complex is harder.
I don't remember what C stands for.
It can be also complicated.
I think it stands for closed.
Close. Okay. So the thing is that the topology here is it comes from the spheres that are glued together. So these are one-dimensional spheres which are glued together by their boundaries. Anyway, so we have a good theory of which describes the topology of those CW complexes, and this is what we use. So, how to compute the first homology group in these terms? So, let's look at one chosen part of this CW complex, which is actually a cubic complex, which means that it is made of cubes which are glued together by the boundaries. So, for example, a cube in this in a complex on this graph will be taking this edge and this edge, the Cartesian product, and here the vertices are just collection of those combinations of those vertices, and we consider them sets because we divide by this, we take the quotient by this permutation group. So we can also see that another nice thing that this complex is locally Cartesian product actually. When you look at it only locally. And another definition of this first homology group is that we have a boundary map, and we look at the kernel of this boundary map, which means that we are looking for one-dimensional cycles in this complex, and we identify them by looking at the image of the boundaries of two-dimensional space. So let me show an example. So suppose that this is our complex. So this thing is filled inside. So when you take this cycle here, this one cycle, so this thing plus this thing plus this thing plus this thing. This thing is, so let's say that it is C. The boundary of C is empty, as you can see, because this is a cycle. And but we have another cell which says say that this is C tilde. But the boundary of C tilde is equal to our C. So this relation here actually means that such things do not contribute to our group because these are contractible. But when we take this C prime here, it is not a boundary of anything. Then it contributes to our group. So it's somehow this group distinguishes like those holes in our space, one-dimensional holes, two-dimensional holes. It comes so, and when we have a torus, for example, then on a torus we have two kinds of non-contractive groups. One goes around this, and another one is here. And H1 of this torus is Z. That's for those two. But okay, Okay, so for those graphs we have some nice description thanks to this topological theory of those complexes, and we know what is the basis of the cycles, of one cycle in this space. So there is one kind of cycles when particles are distributed in a graph, and one particle is self-uniform in a graph. So this is one cycle in this n particle space. Another kind of cycle would be such an exchange of particles. We have two particles on the y graph, and one goes here, another one travels here, which is shown here, and now this particle goes back, and now this particle goes back. So when we have such a process, then we see that they have exchanged. So this is a loop also in this n-dimensional n particle space, and from theory for those complexes, we know that these are all possible one cycles, and this is a good basis for one cycles. So we only have to look for the y graphs and for cycles inside the graph.
When you say particles, you mean that wave functions of these particles are localized on these graphs? In what sense?
We rather look at it as a classical particles which are in vertices. So if you want to have some wave function, then this is another.
This is a space of classical,
Thinking in terms of wave
configuration
functions
space, and wave functions are supposed to be functions on this space.
Yes, yes.
But I think that if you think about hardcore particles, which cannot sit on the same vertex, then the description is the same on quantum level, even if you have some superposition of given particle between two empty vertices.
Because then the terms of wave function is completely different, because you must have the boundary continuity must be satisfied.
Yes, but if you
So
think
you're
about
not talking about wave functions.
Yes, it's not a classical picture now.
Yes, this is purely classical.
Okay, so technical. Anyway, so this exchange corresponds to such a cycle. Okay, so these vertices are the positions of particles. This is 1, 2, and 1, 3. And this edge means that particle moved from vertex 2 to vertex 3. And one particle is sitting here.
So this is something like a tight binding model? That it jumps, or what do you mean by move?
Yes, it jumps from one vertex to
So I can write the Hamiltonian like that I annihilate the particle here and there, create there, right?
Yeah.
So why not to say that in the simple way? That this is just a tight binding model on that graph. That would simplify tremendously the discussion of the problem. I even could write a Hamiltonian for it.
Yes, I mean there are some.
I mean, so many words which can be just written in a one simple equation.
But
or I'm completely wrong.
I'm afraid that this Hamiltonian wouldn't support any anions on this.
Why not?
Why not?
No, the statistics is encoded in the commutation relations.
Yes.
Not in the Hamiltonian.
Not in the Hamiltonian. There will be A and A dagger, and now the question: how do you write the A dagger minus A and this dagger? I mean, it's it will simplify the words classical motion and wave function.
I'm afraid that you cannot encode in the Hamiltonian the topological structure of these graphs.
Why? I mean, the graph is written so.
Of course no, because
of course not.
You just consider the supposedly Hilbert space of functions which are defined somewhere, and then you define the Hamiltonian. But I don't believe you may encode the topology within the
Yes,
Hamiltonian.
of course.
No, but the particle jumps between the vertices.
Yes, but it jumps between two different number states, but not knowing about the topology.
This jump has nothing to do with any
No, we disagree. We disagree.
Yeah.
There are these tunneling terms in the
we will have certain property.
that you can, of course, encode topology in.
The Tij will have a
You will
certain
destroy a particle
property.
here and create it there,
There.
and the links are
Yes.
those links in your graph.
No,
Yeah.
no, that doesn't work.
No, not encode. You may just take into account topology to write some additional.
Yeah, but there is a
terms.
sunder, the sunder over I and J's or whatever.
But if you write
And
down
that
the
sum means that I'm summing over this graph.
No, the graph is not there.
If you write down
It
the
is there.
Hamiltonian, then everything about the system is known. Also the topology. Yes?
Of course.
Yeah.
Everything is encoded in the Hamiltonian
Yeah.
and commutation relations
Yes.
of annihilation operators.
No.
What is not encoded?
So let's take.
Topology.
I think
Topology is
Is
encoded in
encoded
tunneling.
to answer
In
this
tunneling.
question,
The relations
how
of the
do you
structure of the Hilbert
distinguish between
space.
different topologies in the Hamiltonian?
No, no,
We just
statistic.
label the states.
Of course.
Topology is encoded in tunneling terms.
Absolutely.
In tunneling terms between sides.
Yes.
You allow jump from
It is
this
not.
position to that position according to the graph which is.
Yeah,
And you can, if you add,
so there is the sum over I and J which defines these things together with tells me what is the
Yeah.
contribution of a given sum to the problem. That's the IJ.
if you add complex phase also to this tunnelings, then you can encode also external gauge field.
Yeah.
Yeah,
in the system.
whatever. I mean, whatever you need to this. But
Everything can be encoded in the tunneling,
So
and the
that would
statistics.
Can you write the Hamiltonian in the simplest case of this graph?
Yeah,
sure,
Sure.
absolutely.
Without
And
any problem.
it will be different, the Hamiltonian will be different than the Hamiltonian for the graph that has disconnected.
No,
Yes. Yes, it will be different.
Because the
different because
transition,
some
transition
times would be
amplitudes will be
missing.
different, right? That's but
they
the same
may
is if I have
also missing.
again, I mean, but this problem has been discussed at least 70 years ago when people were solving a type binding model, which then became known as a Hubbard model, on the different lattice structures.
Yeah.
Yes.
The form of the Hamiltonian was exactly the same, only the summation was different.
Yes.
And of course, all this permutation group business is there, just the words were slightly the Hamiltonian.
And all this topology of closed loops,
Everything was there.
endpoints, everything is there.
There.
But this proves that the Hamiltonian does not encode the
Yes, of course it's
It does.
yeah, you're right. This is now what Landau called linguistic discussion.
No, no.
What do you mean by Hamiltonian? I mean, you write the letter H, or you mean when you write the Hamiltonian, you have a certain information about the physical system, right? And you call it topology, or the property of that system. It's not worth discussion.
Okay, so let's continue. Okay, so to sum up, we have those one cycles which are, let's like look at this classically when particles move just between vertices, and this is the exchange. This was one exchange, this was another possibility, but this gives rise to some trivial ones because they do not really exchange those particles. It's just one circling around. Okay, so we can use it, use this basis to compute, to count all possible cycles on a star graph. The star graph on each of the edges. So in the principle, we have each of three y cycles here in a star graph. Okay, so we just pick any three edges here, and we have some y graph. So we can pick some another three edges and we get another y graph, etc., but they are not all independent. So we have to take into account some relations which we also know how to describe. So for example, a relation would be take such a y graph and one particle standing here, and such a y graph and one particle standing here, and these two are in a relation. So they actually describe only one and the equivalent cycles in the configuration space. So the number of independent cycles is given by this long formula. This is the number of edges of a star graph. This is the number of particles. So it strongly depends on the number of particles. Okay. So this is the number of anion phases on a star graph, actually. And so one important thing that I would like you to remember is that these all cycles are created by the exchange of only two particles here, and the placement of the remaining particles on the edges. So this will be important in those three graphs. Okay. So if you want to compute higher homology groups, then we are looking for I-dimensional cycles, which would be some surfaces inside our complex. For example, tori, like more.
I'm sorry, but so far these are only the properties of the graphs we are discussing. Will we have, since we are slowly converging to a kind of a fixed point, which is the end of the seminar, are we converging also to some example of how this can be applied to solving any problem in physics? Or we will, or this is just a seminar on the properties of the graph?
It's a mathematical problem.
Yeah, solving the equation is also a mathematical problem. Solving a Schrödinger equation, I am not buying argument that this is a mathematical. No, the question is, are we converging to any quantum mechanical, like any suggestions? Because basically this, I think Professor Maciążek will agree with me, this is eventually a free particles on a complicated lattice. And that is...
No, with hardcore...
With hardcore...
Yes.
Yeah, with...
This important avoidance.
This is important.
Yes, it is.
So does that have any implication, for example, to the conductivity of this lattice?
Yes, so the short answer is that we don't have any example. So it is not rather.
So it even doesn't have the block problem that the free particles on the any lattice have infinite conductivity or something like that. So this extrusion of this hard course is not continued. No, I have nothing against the mathematics. I just don't understand it. But that's in some sense my problem. The question is, I would like to know whether I should still concentrate that there will be a physical problem or...
About the physical problems, we have some ideas how we might...
No, but the ideas, then I also have various ideas, but it doesn't mean I'm going to show them. Okay, no further questions.
Yeah, so hopefully next time. I mean, it is... so on the mathematical side, it's I mean, these results are new on the mathematical side, and this is a difficult problem which has been, sorry, let me show I mean, it's a new thing in mathematics. Like the first results for this were 2008, 2009, and there are very little is known about those things because only two particles were investigated. And the second homology for two particles.
So the final question would be, are those properties of the graphs new? Nobody studied them before?
Yeah, they are new.
Okay,
They were not known before, and this is a very complicated part of mathematics because people up to this time used the Morse theory, which is not applicable for... I mean, it is applicable, but it is hard to use it for larger number of particles, for higher homology groups, and we have some procedures which allow you to compute those homology groups, and which is actually I mean, it's quite good. Here, so there are only the results for now are very small. Like we have only second homology group for two particles, first homology group for any particles. Homology groups for three graphs, but nothing more. And also this is very non-intuitive, so we don't know actually what happens in this Morse theory. And our method gives you like the construction of those cycles, so you can see what happens in these spaces. So so our project is to compute higher homology groups, which are like some higher dimensional cycles in this configuration space. And Arnold computed the higher homology groups for the case of R2, and he noticed some properties that these groups are usually finite. Some of them vanish, so when we want to find some cycles of too high dimension and we put too little particles, then we don't have those cycles. So this is basically what means that the high homology group vanishes. There are some recurrence relations which would be very precious, very desired to find. And also the stabilization. You can have the stabilization with the number of particles with these statistics. So our question is actually, do those homology groups stabilize? Is there some interpretation of different components of these groups? Is there some quantum statistical part? And to what extent they mimic R2? Because we've seen that free-connected planar mimic R2, free-connected non-planar mimic R3, and we would like to know if this is true for up to like 77 homology group. So these are the current results that I've already showed you, and they are there's not many of them. And so our idea is to construct this basis. For example, let's say we're looking for two-dimensional cycles. So we can multiply two cycles and get a torus. So this would be two trivial exchanges. One exchange on a loop, or one exchange on a junction. This is also a torus, but it takes 3 particles. And this thing is also a torus, but 4 particles, because 2 particles exchange here, and 2 particles exchange here. So our idea is just to look for those tori and see what the number of those tori is in this big configuration space. So the simplest example is 3 graphs. And the idea is to put the number of particles on one star graph and the number of particles on another star graph, look at the all possible 1 cycles and multiply those cycles. And then we get a number of tori. So we can put 2 particles here, 2 particles here, and we multiply the numbers for the star graph which we had before. Then we get 3 tori. When we put more particles, then we have some double counting, which we know how to deal with, and we have 17 tori.
And is this a new result, or this was known before?
So okay, it's
17, for instance.
This 17. I mean, there was some procedure from Morse theory, but it was hard to obtain this 17 from this procedure. So it's more tractable. This approach is much more tractable. So for any star, for any 3 graph, we just find all star graphs inside it, and we get one formula, but it's like a closed form. So this is a new result. So this is what hasn't been found yet in other works. We can compute all higher homology groups, just multiply more cycles. So for 3 graphs, we know that those groups do not stabilize. Also, this higher dimensional homologies also vanish, as we have for the plane. Okay, and those groups do not depend on the connection between star graphs, which is maybe somehow counterintuitive. Okay, also we have some.
What can I have a look at the previous case? What it means that homology groups are free?
These are just copies of Z. There's no torsion. No Z2 part. Every homology group is it's like Z power of some it's just so this is a free application. Okay, so we also have a numerical procedure of how to compute other homology groups on other star graph, on any graph actually. And this uses the Morse theory. So this is so to compare our results to some known procedure which you know that works.
And this K33 is bipartite graph?
Yes, yes. K33 is complete and free.
Like two teams of players playing each game against the opponents.
Yes.
So 3 tennis players in the game. Yes.
So, okay, you see that the complexity was very fast. So, the biggest thing that we could reach was 6 particles on K5 graph.
And this dimension, you don't have analytical formula, let's say, for arbitrary K.
Well, here we have an analytical formula, and here we have an analytical formula. Here there are some things which we cannot explain yet.
And have you checked whether those sequence of integers are known in famous catalogs of integer numbers?
No, I don't
Sloan.
I haven't seen them in the papers.
Have you checked in the famous Sloan webpage?
No, not yet. No, I haven't.
Why there are minuses?
Sloan.
It's minuses because this group is zero.
Sloan catalog
doesn't make sense to include this. Okay, so I don't know. I don't have too much time, so maybe I wanted to show you this procedure, how this procedure works for some different graphs. So it basically comes to counting y graphs. We want to take out the y graph from a graph and see to what number of parts and we distribute particles among those parts. So we are putting particles in these. So we have those analytic formulae for for this K4. We can also produce such formulae for K33. So the biggest difficulty is, are there any other 2 cycles than those torus that we had, like multiplications of cycles? And the answer is yes. So an example would be such a graph, and the second homology is Z. The first homology is Z6, so we see that genus is free of a 3 particle configuration space on such a graph. So the question is, if we have only tori. So the answer is no, we don't have only tori. And our example, it's nobody has found this example. There were some claims that there are only just 2 graphs which don't have this property, but we have found another graph and a whole family of another graph, which is also, actually this example is also a new valuable result. So you see that we put 3 particles, this is a 2-dimensional surface, this is 3, of genus 3, and we can check that this is the triplet. And we can produce like a whole family of
So, Łukasz, you can even buy such pretzel nowadays to have a physical application. Yes.
Okay, so in our further work we want to compute the homology groups for particles on one connected graph. This would be a continuation of the work on those 3 graphs. Question about the possible torsions. The torsion is a part which is not the free part, but Z. Okay, like the finite numbers of group elements, which also it is not known as it is a big question for those configuration spaces. Question if there are any graphs where the homology group stabilize. So we think that there are none, but we don't have a proof yet. Maybe generalize this procedure for any simple graph. And also, we have an idea of how to, we might construct a physical model for H2. Because the second homology group is isomorphic to a second cohomology. And the second cohomology, the elements of representative of the cohomology group are closed, non-exact two forms, and they can describe Dirac manifolds. So we might have some Dirac manifolds in this configuration spaces. And the question is how to construct the proper gauge field and proper connection form.